Hello everyone, my name is Ali Ababisani. I'm honored to present my recent project about estimation of an intelligibility measure for consonants in a speech. The usage of this model is to help in the case of a speech-based tests for hearing assessment. When audiologists want to include a speech in the process of tuning a hearing aid, they can use this model to assess the intelligibility of speech tokens that they want to use to present to the hearing, the subject who have hearing loss. I will go ahead and state the problem statement and the estimated model and the results. Generally, we know that the hearing impairment is a serious problem. We can look to the normal hearing speech perception, and we can determine the primary cue region by performing experiments to like low pass filtering, high pass filtering, and time truncation to find out the time frequency window that is related to the primary cue region of the speech syllabus. Based on the experiments, we observed that we can assign when we assess this, present this to the normal hearing subjects, we can assign an intelligibility measure related to background noise. So if the noise is above that threshold, the recognition score will go down, and if the noise is below that, the recognition will be very good. If we enhance that cue region, normal hearing listeners will respond to this enhancement, and they with higher SNR, with higher noise, if we amplify that cue region, the score can enhance the score. For the hearing impaired subject, we observe that the confusion patterns for hearing impaired is very similar to normal hearing. Based on our previous experiments, we also observed that the pure tone threshold based amplification is not always helpful. For example, we need a more complex approach than just compensating for the audibility of the speech sound. Also, we observe that the noise thresholds plays an important role for hearing impaired consonant recognition. So the motivation behind this project is to provide a perceptual measure for speech phones in background noise, and also identify the appropriate amplification amount for target phones. So when you have a new sound, you have a speech syllabus, you assess with this model and in the background noise, and see if determine if the sound, if this speech syllabus is intelligible or not, and if it is not, how much you need to amplify to bring it up to the intelligibility. Here is a study that we did a while back. This shows that, for example, if we provide the hearing amplification, the insertion gain based on the hearing loss profile, as you see, it can improve like 30%. In this study, it improved 30%. It was doesn't matter for more than 50% of the cases. Like the sound didn't have the error at all. But for 12% it degraded. And if you can see this plot here, these are for different subjects. You can observe that the error and the degradation or improvement here is across all of the sounds. So these are the sounds down here. You have both male and female talkers and different SNRs. So we cannot say a specific, we cannot provide a specific rule to generalize the recognition in this fashion. We want to find this perceptual measure. We call it SNR 90. So SNR 90 means that, for example, if you provide the sound for normal hearing listeners, if you increase the noise at some point the recognition score will drop. And if we average, for example, presenting the same sound to, let's say, 40 different normal hearing listeners, and we average the score, we can observe curves such as this on the lower panel here. And if we look to the average error, it starts from 100% correct on the right, and it goes down at some point. At the 90% level, we can assign that as a SNR 90. So that's the label for perceptual measure. This upper panel here shows that if we align the sounds, the recognition based on the SNR 50, we can see some of the sounds having being like outliers, so we should not include those sounds in the experiments. But we keep the sounds that we have a steep difference between changing a little noise, but the score can change dramatically. So that this is a way to prune the sounds that we want to use. Now we want to see if how we can basically use this perceptual measure that is related to the noise and also related to the primary cue intensity of the primary. So this is an experiment with hearing impaired subjects. These are the audiogram profiles for 4 subjects. We have 8 curves here, and these are the average curves, the average recognition across all of the sounds that we presented. The blue curve is the sounds that have higher SNR90, that means less clear. The red curve is the sounds that have lower SNR90, so more clear sound. So basically, you see across all of the subject, even though they are very different in their hearing loss profile, this SNR90 is a good measure to reduce the error. So for all of and the x-axis here is the SNR. So you see for all of the cases, when you change the SNR90 for hearing impaired subject, the error goes down when when we enhance the SNR90. So here we train the model. We want to estimate the SNR90. So the goal is to train to provide. So the goal is to automatically estimate this SNR90 based on the sounds that we have. So the problem here is that we have a limited number of sounds because the sounds, this SNR90 assessment is basically coming from time-consuming experiments. It's time-consuming and very expensive, so we have a limited number of sounds. To be able to train a model, we have to augment the speech. So we have to apply some distortions to the sounds, so we come up with more training data to be able to train the model. So the distortions that we apply can be changing the duration for consonant or vowel, changing the pitch, and applying some filter, low pass or high pass filter. So each of these distortion can produce a new sound, but here we want to make sure that the sounds are intelligible. So here are examples. For example,
Sha.
This is the original sound,
Sha.
and this is let's say a consonant duration increase.
Sha.
And this is a high pass filter.
Sha.
So these are the most extreme cases. So we want to make sure that the most extreme distortions don't change the intelligibility. To be able to assess that, we basically look to the most distorted cases and took those sounds and run another experiment for those extreme distorted and see how the SNR90 is changed. Based on this plots, you can see that for some of the sounds, for some of the distortion, for example, here in the low pass filter in the upper left, some of the sounds are saturated. So we ignored that distortions that saturates the the SNR90. So it's by saturation, I mean going above some level. Here, I want to see if the SNR90 goes above 6 dB. If it goes so, I ignore that scheme, that distortion scheme for that particular sound. Here is the data preparation. We basically remove the distortions that saturated the SNR90. For each consonant, we divided the tokens into train and development and test portions. In this table, you can see the from each sound, what are the number of total sounds that we get for each training, development, and test. And basically, the talkers were separate in each portion. So there are not non-overlapping talkers. And also we train separate models for each consonant. So this is the architecture. We basically use a convolutional neural net with starting with 3 layers, and it can increase to 7 layers. This is based on time delay neural network introduced by Weibo at 1989. The input level is 320 dimension log magnitude short time Fourier transform. And these are the weights that we have for each layer of the CNN, and we have 2 fully connected layers. We have average pooling, and this is a regression model, so uses SNR90 as the label. One thing that I forgot to mention is that when I get a new label for SNR90, I have the original SNR90, I have the most extreme case SNR90. I basically label the sounds in between using just linearly interpolation. And here I have all the labels for regression, and I have the loss as mean square error, and the optimizer is stochastic gradient descent. Hyperparameter tuning is based on the development data. We basically have this kind of layers, and the hyperparameter includes the number of layers, the weights of the layers, batch size, learning rate, and dropout for each model. So here are the results. Basically, you can see for each consonant, we focus on a stop consonant in this project. For each consonant, we have the original number of sounds. For example, pa has 6 original sounds. This is the average SNR90 based on human, and this is the average SNR90 based on ASR. The ASR here is the Google Cloud speech-to-text model, phone model. Basically, the way that we assess SNR90 is that we present the sound to the ASR, and if the output word includes the consonant, we counted that as a correct recognition. You can observe that the ASR is very much different than human recognition. We also provide the perceptual evaluation of a speech quality score here for the as the average for all of the sounds, and these are, as you can see from the number, these are good quality sounds. So ASR bias is basically here. We have the variance for the ASR. It's very high regarding to the estimation of SNR90. This is our model's test mean square error. If you compare this to the variance of the ASR, you can see that our model is very good, very accurately can estimate the SNR90 less than 2 dB square difference between the estimated and the original SNR90 based on the mean square error. So this is a good model. We can, in conclusion, we can say that the SNR90 is related to intensity of the primary cue. The models that develop here based on convolutional neural net to estimate the SNR90. So these models can be used to evaluate a speech syllabus before using them in a speech-based speech perception for humans. So that will keep, if you use this model, it saves you time and money to run all of these experiments to assess the intelligibility for a speech sound. Also, speech augmentation, we use those to boost the training data adequately to be able to do a deep learning model training. And we basically develop this model outperform the ASR, and that's basically the only available baseline. So this is a new kind of approach to this model. Thank you so much.